We continue working through Chapter 10. We've already been introduced to the concept of correlation as a synonym for association, and we've looked at linear relationships between paired data, and we've looked at the linear correlation coefficient R. In this second section of the chapter, we're going to look at linear regression. This section is going to focus on finding the equation of the line that best describes the relationship between x and y when there is linear correlation. This best fitting straight line is called the regression line, and its equation is called the regression equation. So we are going to be working with paired numerical data, paired x and y values that exhibit some sort of linear relationship when we look at the graph of those ordered pairs, which we call a scatter plot. And what we're going to be working on in this section is finding the equation of that line that best captures that linear relationship. And we call that the regression line, line of best fit. We also call it the least squares line, many other names, but regression line is what we're going to be calling it for the purposes of our course. You might remember from your previous algebra courses that the equations of lines can be written in several different forms: standard form, slope-intercept form, point-slope form, to name a few. What we're going to be using in this section is the slope-intercept form for the equation of a line. You may remember from your algebra courses y is equal to mx plus b, where m, the coefficient of the x variable, is equal to the slope of the line, and b is a constant that represents the y-coordinate of the y-intercept of the line. Well, what we have here is slope-intercept form, but we purposely swap the two terms on the right so that the x term is listed second and the constant term is listed first. And the only reason we do this is so that we can match the output that technology is going to give us. So remember, addition is commutative. You can add in any order and you still get the same result. So it's still that y equals mx plus b form, that slope-intercept form. Here we have these real numbers. B sub naught is the y-coordinate of our y-intercept, and b sub 1 is going to be like the m, it's going to be our slope. Now on our TI-83 and TI-84 calculators, we are not going to see this notation, the B naught and the B1. Instead, we're going to be looking at A and B on our output screen. So anytime in this section where you see the B naught reference, that's equivalent to A on the calculator. And anytime you see a B1 reference, that's equivalent to B on our calculator. Now let's talk about the two variables, x and y. X is the independent variable. In statistics, we say that it is also the explanatory variable. Y is the output variable, which we call the dependent variable. X is the predictor variable, so that's another way of looking at x. And then y is the response variable. So lots of different names. Basically, our selection for the value of x determines the corresponding y value. I also want to talk a little bit about this little hat symbol here. The hat symbol is intentional. It is a way of us differentiating between y values that are predictions that fall strictly on this line versus y values that come from the original data. So the calculators don't know any different, but this should say y hat as well. So again, y hat is a predicted value of y. It's whatever falls on the regression line, but it may not come from the original data. Alright, you might remember that I mentioned in the last video that, oh come on, get out of the way, that's not working, that we're going to be looking at linear correlation coming from sample data, so that R is representing the linear correlation coefficient for a sample, and it is a sample statistic. Well, we're going to differentiate as well with the symbols that we have for the regression line. B sub naught is going to be the y-intercept coordinate for the sample regression line. B sub 1 is going to be the slope of the regression line from a sample, and so like we saw in the previous slide, this would be the regression equation for the sample. We turn over to using Greek letters. This is the capital letter beta from the Greek alphabet. Beta is being used here in lieu of the lowercase b's to label this as data that's coming from an entire population. So if somehow we have access to census data for the entire population of interest, we just want to differentiate with symbols appropriately. So this is also missing the hat symbol here. Definitely should be there. I'm not sure why it's not showing up. In order for us to talk about linear correlation R, in order for us to talk about a regression line, we have some requirements, which we talked about in our last section as well. Our data does have to be numerical, has to be quantitative, and it has to be paired. And ideally, it should come from a simple random sample so that our data is as representative for the entire population as possible. We also should build a scatter plot to make sure that we're detecting a linear pattern, because if we can't detect a linear pattern with our eyes, certainly there's no point in calculating any R value or talking about a line of best fit. Third, we want to make sure that if we see any potential outliers, really extreme low values or extreme high values, that we examine them more closely and take a look at whether they're legitimate and if they should be removed. Outliers can have a very strong impact on the regression equation calculations, so we want to make sure that if they are legitimate, that we're aware of them, and if they're not legitimate, that we have a way of removing them before trying to find the line of best fit. In addition, we want to make sure that when we're looking at the scatter plot of our data and we're detecting that there's a linear trend, that linear trend isn't getting either more defined or less defined as we move across from left to right. So for example, we don't want points to be very tightly wound around a linear pattern and then suddenly they start spreading out, or vice versa. We don't want points that are very spread out and suddenly they start taking on a linear pattern as we move from the left to the right. Let's look at some formulas for how to calculate the slope of the regression line as well as the y-intercept. So these are manual formulas and they are on the formula sheet in our course. You will not have to find these two values manually, but it's always a good idea to know where they're coming from so that we can understand how they're calculated. Again, the regression equation is y equals mx plus b, but in this course we write it as y hat, which is the predicted y value, is equal to b sub naught, which is our y-intercept, plus b sub 1 times x, so that is slope times x. First we calculate the slope. The slope is equal to that linear correlation coefficient r multiplied by the standard deviation of the y values divided by the standard deviation of the x values. So it's a pretty simple calculation as long as you already know what r is and you know the two standard deviations for the x and the y variables. The y-intercept, on the other hand, is found by taking the mean of all the y values from our data set and subtracting from it the product between the slope, which we found above, b1, and the mean of the x values from our data set. Not a huge calculation. We do have to calculate r first, calculate the standard deviations, calculate the two means, but as I said multiple times, we will not be finding these manually. We are going to be able to find these with our calculator. These calculations should be taken out to 3 significant digits, and that is, again, so that we can have a way to compare it to some tables. And we saw this example in our last lesson, in lesson 10.1, when we were talking about correlation. We have pair data, which gives us the lottery, jackpot, Powerball amounts versus the ticket sales. So each one of these columns represents a pair. The jackpot numbers are the X values, the ticket numbers are the Y values, and there are 9 pairs total in this example. Again, we saw in our previous section that the scatter plot indeed shows a linear trend, and what we're trying to do in this section essentially is trying to decide what line captures this trend most closely. So you can imagine a line that starts at this point and then maybe goes through that point, but it kind of would miss all of these below. So then you might say, all right, let me start with this point and maybe connect it to this one, but that might not capture what's going on down here. So there is a program, there's an algorithm for finding that line of best fit. There is something quite powerful that's happening behind the scenes, and that is where our formulas from the previous slide come from. So if we apply that algorithm, if we apply that formula, that program, we are all going to come up with the very, very same line that captures this trend the very best. So we have evidence that there is linear correlation. We see a linear pattern. We don't see any outliers. Nothing seems to stand out from the rest of the data. It means that we're good to go to calculate the y-intercept and the slope of the line. Lots of different computer programs and applications will give you the very same results. I want you to focus on this part of the screen. This is what the output for the TI-83 and 84 calculators look like. In fact, we saw this output in our previous section. It's just not scrolled down far enough for you to see R. But R is on the very same output screen as A and B. I want to pause for a moment and just remind you what A and B stand for. A is the y-intercept, B is the slope of the line. A is the y-intercept, B is the slope, and then if we had a calculator and we clicked on that little arrow to go down, we would see the R value as well. So here is what that linear regression equation would look like for the example with the jackpot data versus ticket sales. We saw that on that calculator screen, the y-intercept A had a value of approximately negative 10.9, and the value for B, which is our slope, had an approximate value of 0.174. So here is the equation of that regression line. What we're going to do here is we're going to superimpose that line that we just found the equation of onto the scatter plot. And this is the result of the regression calculation. So you see that the line really only passes through 2 of the points, and the rest of the points don't fall on the line, but there's no line that can capture all of the points. This line here is the one that best represents the linear trend in this example. So this line right here has the equation y hat equals negative 10 point whatever that was plus 0.1 whatever that was x. I don't remember from the previous screen, but that is that line graphed over the scatter plot. Now, when we're working with regression, the main idea is that we can use the trend that has already been established by the data that has been collected and use that to make predictions about what we think will happen with other x values. So I want to go back. Let me see if I can go back this way. If I were to go back to the scatter plot, obviously these red dots come from the observed data. This has already been collected from what has occurred in our study. But what if I wanted to ask the question, I wonder if the jackpot amount was $275 million. So right around where my cursor is now, $275 million. What would that tell me about the ticket sales? So at $275 million, I could go vertically up to this regression line, and I see that there's no ordered pair there, but there is an ordered pair that is on the regression line, right? So no red dot, but I can use that then to go horizontally over to the left, and I would say that close to 40 million tickets would be predicted to be sold if the jackpot was approximately $275 million. So this line then becomes a prediction line. It's a way of us making predictions for different values of x based on what has already been observed with the data in our sample. So sometimes we'll be able to use the regression equation to make predictions, and sometimes that's not a good idea. So how do we tell the difference? Well, it all comes back to the value of r. We looked at how to determine if we have strong evidence of linear correlation by comparing the magnitude or the absolute value of the r calculation that we came up with to a table of critical values. If the absolute value or the magnitude of r is at least as large as the critical value on that table, that means we have a good model, we can use it to make predictions. However, if the calculation of r comes up with a magnitude or absolute value that is less than the critical value on table A6, then we would say that's not a reliable model, and instead of using it to make predictions, we're going to use something else. In fact, what we're going to do is we're going to use the mean of the y values from our observed data set as our prediction. So on the next slide, we're going to summarize what I just said in a little bit more of a visual way. When we're predicting values for y based on a chosen value of x, there are two ways to do that. One is to use the regression equation by just substituting the value of x that we have wanting to make a prediction for, just substituting that into the equation to get the corresponding predicted value of y. But we only should do this if we have evidence of linear correlation. And that, of course, happens if the magnitude of r is at least as large as the critical value on table A6. If we don't have an r absolute value that is at least as big as the critical value on the table, that means we don't have a good model, and no matter what x value we want to know something about, the predicted value will be y bar, which is the mean of the observed y values. So in other words, if your regression equation is not a good one, then don't use it to make predictions. If you do not have evidence of linear correlation, then the best you could do for a prediction is to use the mean of the observed y values. So in this PowerPoint presentation, they go into two examples just to illustrate a good model versus a bad model. The first example here with letter A is the one that we've been working on all along. We already know it's a good model because we found that the linear correlation coefficient R, which was in excess of 0.9, was bigger than the critical value on table A6, which was only 0.666. So we know we have a good model. If we want to make a prediction for the number of ticket sales based on an assumed lottery of 625 million, so this would be our x value here, we simply would have to substitute 625 in for x into our regression equation, which we'll see in the next slide. On the other hand, for the second example, they're saying, please predict the IQ score of an adult who measures 175 centimeters in height. Well, there isn't really an assumption that IQ scores are linear, have any type of relationship, let alone a linear relationship with height. So if IQ scores and height are not really related, then we shouldn't be using a regression equation to make any predictions. So in the case of example B, our best prediction for y will be whatever the mean of the y values turns out to be for that data set. So again, when we have a good model, take the x value that you want to know something about, substitute it into the equation. In this case, when there are $625 million in the jackpot, we expect ticket sales to be approximately 97.9 million tickets. And again, that's just the predicted y value when we substitute this number in for x. Again, we do this because we have a good model. On the other hand, in the case of IQ scores and height, we don't have linear correlation evidence. Therefore, regardless of what x value we want to make a prediction for, the best prediction will always be the mean of the y values, which in this case, let's say is 100. That's the mean of the IQ scores universally. We're going to review some terminology very quickly. We've already talked about what an outlier is in general. In a scatter plot, an outlier is a point that just doesn't seem to fit with the rest. It doesn't follow the same pattern. So it's either very low, very high, or just kind of stands out there on its own. An influential point, on the other hand, is a point that strongly affects the calculation of R, or strongly affects the calculation of our regression line, whether it's the slope, the y-intercept, or both. And so we call it influential because it influences those calculations. Here's a visual for what an influential point is, and in this case I think this is an outlier as well. So here are the 9 pairs that came from the example that we've been working on throughout the chapter, and this is the regression line that we found for these 9 ordered pairs. Well, let's say that in addition to those 9 ordered pairs, we had this little guy right there who just did not seem to go with the rest. When we add that additional ordered pair to the calculation of our regression line, look at what happens to the regression line. It completely goes chasing after that point. So we went from a line that really captured the trend very well. It had positive slope. It really seemed to capture where that marker would go if we were trying to trace these points with a thick marker. But just with the addition of that one ordered pair, the regression line now goes chasing after it, and it no longer captures the overall trend of what those original 9 data points were doing. So that one additional point really threw off the calculation. Therefore, we would say that it is an influential point, and yes, in this case, it would also be an outlier. Lastly, let's talk about what a residual is. We have talked about the fact that our regression line is used to make predictions. So we choose an x value, we substitute it into the equation, and out comes a predicted value of y. Well, that could very well differ from an observed value of y from the data if we were to look for that precise x somewhere in the data. So that is what a residual is. It is the difference between an observed value of y and the predicted value of y for the same x value. So same x, what is the observed y versus what would it have been predicted? using the regression line. So it's a vertical distance between those two y values. Here's a different example. So we're no longer looking at the 9 ordered pairs from the jackpot data, for instance. It's a much smaller example. We only have 4 ordered pairs. But here are the 4 ordered pairs where my cursor is. Here's 1, 2, 3, 4. Those are the 4 ordered pairs. This here is the regression line. Now you might argue that the 4 points don't seem to follow a linear pattern, and I would have to probably agree with you a bit. But if we agree that it at least exhibits a little bit of a linear pattern, this would be our regression line. And let's take this point for instance. Here is an x. Okay, this x value is 12. I know that from the table. The x value is 12, and the corresponding y value is 24. So this is the ordered pair 12, 24. Well, 24 is the observed y value. However, if we were to follow vertically down to the line, this point where my cursor is also has an x value of 12, but it only has a y value of, let's say, about 13 maybe. So that would be the predicted y value. So the difference between those two is 11, right? 24 is the actual y value. 13 is the predicted y value. If we subtract those, we would get a difference of 18, and that vertical distance is what we call a residual.